Okay, folks, let's get started on determining currents in the BJT. So a BJT is basically a current amplifying device, right? It turns a small base current into a large emitter to collector current. And so we desperately need some equations which will tell us what these currents will be as we optimize our design for the BJT. The photo to get us started today, as we head down this path, is a photo of a heterojunction bipolar transistor. A heterojunction means that it's not all silicon, meaning that it could be gallium arsenide, aluminum gallium arsenide, several types of semiconductors that form junctions between dissimilar materials, hence the term heterojunction. And this device is grown epitaxially, meaning that it's grown up on a substrate, one material layer at a time. And it's interesting to view this thing, and it gives you an idea about why BJTs are so useful in high current applications. So if you look at this, here's the base, here's the emitter, here's the collector. And in this device, the base is really thin. So it comes in, makes this contact, and it's somewhere in here, a really thin layer that you probably can barely even see here, where it makes contact in between the collector and the emitter. Okay? You also notice here that the emitter and the collector contacts is a huge metal contact, meaning that you can drive a lot of current through this thing. And the reason why this thing has such high current capability is that if you look at this, think of rho L over A here. My area, okay, for the resistance, as I calculate resistance through the device, is this kind of cross-sectional area here. Okay, so I'm basically driving current down through the device, and this would be my area. Okay, and so the area is large because I've got this large sheet. And so that's good because if area is large, that drives down resistance. And then my length is the width of which I'm traveling through the current with. And so if it's the base that I'm trying to get the current through, then you can see the base would be really thin here, right? So basically, if you look at a BJT, you could see from the aspect of just basic resistance, if you have a really good metal contact here, good metal contact, and good semiconductor underneath here, the area that has to control the current can become a very low resistance, and you can easily get current going from the emitter to the collector. Okay, now before we start this lecture today, you must be absolutely solid on some of the concepts we talked about last time. You should be able to understand how the holes for a PNP BJT get from the emitter into the base and across to the other side, and you should understand all the different current components going on as well. And so pause the lecture, briefly review this, and make sure this all makes sense. Especially also what we did to get good BJT design in terms of making this heavily doped, this lightly doped, and having a narrow base width. If you remember all that, you're in good shape. If not, go back and just review Part A of the previous lecture. Okay, so let's get started now. So our goal today is again to calculate currents for the BJT. When we do that, to simplify the math, we're going to make a couple key assumptions. The first key assumption is that holes diffuse from emitter to collector and drift is negligible, meaning that there's no electric field in the base. So we're going to assume that diffusion dominates the current flow across the base, which is a fair assumption as we'll see. We will also assume that the emitter injection efficiency is 1. That means the emitter current here is all holes, meaning that this component is so small that we can ignore it. Assume that it's basically all holes, and the number of electrons coming back this way are so small that we'll just keep track of the holes. We will also assume that we can neglect the reverse saturation current for the collector. Reverse saturation currents are really small, so this base collector reverse saturation current, not even going to worry about it. And we're going to assume that our area is the same in one dimension here. So the area here and the area here and the area here, it's constant. And so we can assume our currents are flowing through this in one dimension. They don't have to spread out or confine if the area was constricting or expanding. The area is constant for each section of the device. And we'll assume that all currents and voltages are at steady state. So we're not talking about AC operation yet. Now, beware. Things will get very complicated. But at the end, I promise you they're going to end up to be elegantly simple. And so first we're going to go through the complicated part, then we'll make it really simple in the end. So let's begin like we did last time, just with the emitter base alone. Okay? Now, recall that our emitter base is for a P plus N P BJT. The emitter is heavily doped. The base is lightly doped. And remember when we did P plus N junctions, we looked at the change in carrier concentrations at the edge of the depletion region. And so, for example, if we looked at the hole concentration into the N-type side of a diode, we plotted as follows versus distance into the N side. We said that this function, delta P xn, okay, was equal to delta Pn, which is the excess right at the interface. So I have my, right here at the interface is my delta Pn, okay? And then that falls off exponentially with distance. So as I go further out and increasing distance x, the concentration falls off exponentially, which makes sense because what I have is I have holes diffusing over to this side. They find themselves in N-type material, and this is just showing them recombining, and eventually they return, as you go far enough out, to the normal minority carrier hole concentration in the N-type material. And that's shown with this equation here, where here's our exponential decrease with distance into the N-type side, and the excess, delta P sub n, is just calculated just like the diode equation. It's P sub n, what's the normal concentration at thermal equilibrium, and then this part of the diode equation, which says that if you go to forward bias, it'll go up, as you can see here, and if you go to reverse bias, this term disappears. I have minus 1 times that, meaning that it will go to 0. So let's review this again and repeat just what I said there. The diagram I have it right is for if voltage is positive. So this is positive voltage, you have an excess of holes showing up here. If voltage equaled 0, what would this diagram look like? Okay. Well, we know that if voltage was equal to 0, right, then this term here would be 1, V equals 0. I would have 1 minus 1, which is 0. So delta Pn would be 0. I would have no delta, and I would just have P sub n. So at V equals 0, my concentration would be just P sub n, right? Meaning it's not changing. I have the same amount that are diffusing over versus the amount that are drifting back to the other side. And just like we said, a diode with no bias on it, there's drift and diffusion current happening all the time, but they cancel each other out. Next question, and this will be important as we look at the base collector region of a BJT. If the voltage is negative, it'll look like what? What will it look like? Well, look at the equation here, okay? That gives you all the answers you need. If you look at the equation here, okay, you notice that for that case, let's see if I can erase this. It doesn't want to let me erase it, so I'll just write over it. For that case, if voltage is negative, then this term is not 1, but it becomes 0. So then I end up with P sub n minus 1, which is equal to minus P sub n, right? Well, if delta P is minus P sub n, and I look at this function here, I have P sub n minus P sub n, which is 0, right? And so when you reverse bias this thing, the concentration profile, if you recall, looks like this instead. And so as you go further distance in, you get to the normal concentration way out here, but right here at the edge it goes to 0, and that makes sense because this is would be a reverse bias diode in this case for negative voltage. And for a reverse bias diode, we know that at the depletion edge, every hole that's created as a minority carrier hole on this side will wiggle around, fall off the cliff edge, and go to the other side. And only until you go further away do you see holes that are created that won't go too close to the cliff edge and fall off to the other side as drift current. So again, this is a little bit of review, and it'll be important for understanding both the emitter base and the base collector side of the BJT. Okay, so now let's go back to all 3 terminals and start looking at our Fermi levels and how they shift. So here's a BJT with no voltage applied to it. No voltage applied, our Fermi levels line up, right? And here is the BJT in normal forward active mode, where we have forward bias the emitter base, right? Positive voltage here brings the bands down, negative voltage bands up, and so you can see the offset between the Fermi levels, which is an energy band diagram is Q times voltage. That gives you energy offset. And I can see that my collector base is reverse biased. Again, I have essentially positive on this side, bands down, negative on this side, bands up, and you can see that this is now shifted in this direction in terms of the Fermi levels. So, based on what we learned for the previous slide, here's a question you should be able to answer. Where in the base for the diagram at right should we see an excess of holes or no or zero holes at all? Let's think about this. Well, if this is forward biased on this side of the emitter base here, that means I'm building up an excess of holes here. I'm bringing over holes, and they're going to build up an excess at the left side. Now, the base collector is reverse biased, right? So based on the previous side, we said that the concentration on this side will drop to zero. So there will be sorry, I'm back. My calendar popped up on my my iPad reminding me that class was going to start here soon. So let me get back to this lecture though. So again, I was saying that on the on the base collector side here, concentration is zero. So I have an excess on this side, and I have zero concentration on this side because this is reverse bias diode. They all fall off the cliff. And here I'm diffusing over an excess because I've reduced this barrier here, and I end up with an excess. Excess here, zero on this side. That's going to be. So, what we want to do then is take the same analysis we did for just a P plus N junction and apply it not only to the P plus N junction here, but also to the NP junction on this side. And so we're going to introduce our terms delta PE and delta PC. Delta PE will be basically, as you put voltage on this side of the BJT, what's the excess that shows up right here at the emitter side? Hence it's called delta PE, excess of holes at the emitter side. And then we also have, on the collector side of the base, delta PC. What's the excess we have on the collector side? Now, I know on the collector side this is reverse biased, so we don't have an excess, we have zero. And we'll see that the equations work out anyway. So I've got my term for delta PC, which is dependent on emitter base voltage, and delta PC, which is dependent on collector base voltage. So under normal conditions, when we're operating this in amplification, we can simplify the equations as follows. And it makes sense if you look at the diagram I have here, and based on the previous slide, or the equations. So we know for the emitter side, we have delta PE, and that's an excess, because we have the emitter's forward bias, and so this term is much larger than this term, so I get rid of the minus 1, and I have delta PE is just equal to this as a result. And I can do the same thing on the collector side, knowing that it's reverse biased, so this term goes to 0, and I end up with minus P sub n, so delta PC is minus P sub n. P sub n minus P sub n, there's my zero concentration. So now you can see your whole concentration across the base. Here's an excess, and it goes down to 0 on the other side. So you already should be looking at this and saying, wow, I've got a concentration gradient here, right? I've got an excess on this side, 0 here, and so diffusion should be driving my holes across the base. So if diffusion is driving holes across the base, then let's apply the diffusion equation in the base. And the answer is why? Well, if I basically know, if I want to know why to do that, if I basically know the concentration profile across the base, then the diffusion equation can help me determine what the profile solution is, how much current will actually be flowing. Now, this is a second order differential equation. We'll talk about that on the next slide. We'll talk about how to solve that. But just look at this and see if it makes sense. So differential equations give you general behavior of some kind of system. They don't give you the exact solution, but they tell you general behavior. And if you look at this, look at the effect of some of the general meaning here. If you have a smaller LP or a larger delta P. And so this is basically not change in concentration, but this is the second derivative. What is the change in concentration. And so it's not necessarily slope, which would be constant, but it's something like this, saying that my slope is changing with time. So how does my slope, with distance, how does my slope change with distance? And it's saying that's equal to the excess I have divided by LP squared. Well, does that make sense? Well, think about that. If I want to have a larger change in the concentration with distance and a change in the slope with concentration with distance, I'd like to have a larger excess at the interface. And the other thing is that if my diffusion length is small, this term goes up as well. And that makes sense, because if my diffusion length is small, holes cannot go as far into the base before they recombine, so the concentration will fall off more quickly. So if I have a smaller LP, they'll recombine more quickly, and my concentration profile will look like this instead. And so this is just showing some general behavior for the base in terms of this general diffusion equation. We already had one solution for this when we back when we were doing in chapter 4 of the book, and you learned in semiconductor physics, is that this differential equation could be solved, and you could come up with the exact equation which predicts the concentration profile versus distance when you have an excess. And that's the same thing we used on the previous slides to map out the excess of holes that are diffusing over and appearing on the other side. Okay, so now let's solve this differential equation. And in our program, we no longer offer differential equations as a pure math course you get to take. But differential equations are actually pretty easy to solve. So let me show you one example here and reinforce with you that differential equations are not that difficult to solve. So here's my differential equation, okay? And again, the differential equation just gives you general behavior of some type of system, but it doesn't give you the exact solution. So the next thing I do after I have my differential equation, identify, of course, that's a differential equation, is I put my derivatives in rank order. So basically I've got, here's my second derivative of this function, so d squared dx squared of this function. The first derivative doesn't exist, and then I've got this constant term here where I've just the function times some constant here, okay? So I do this, and then I basically go to a book. I say, okay, here's my differential equation. I look for in a book for a differential equation as some function of second derivative of a function, first derivative, no derivative, set it equal to 0. And I basically look in there and I pull out the coefficients I have, okay? And so I have a coefficient, for example, a coefficient b here times the function. Well, for here, it's 1 over LP, right? So if this is just the function y, okay, then I have some constant b times it. Well, in this case, that function y is multiplied just by 1 over LP squared, okay? And then I see if there's anything out with the first derivative. The first derivative doesn't exist. There is no d delta p dx. There's only the second derivative. And so then I know that a is equal to 0 because this does not exist. So then in the same book, what it's going to have is it's going to have you basically just do this quick check. It says, is a squared minus 4b, the coefficients in front of these, the non-derivative and the first derivative, are they greater than 0? And so I do a quick check. I say, well, a was 0, and I have 4b. Here's my 4. b in this case was 1 over LP squared times my function here, okay? And so you'll find then is that I have a minus times a minus. That gives me a positive. 0 squared plus a positive is greater than 0. The answer is yes. And then in the book, it will tell you that the general solution is a second-order homogeneous differential equation with constant coefficients and 2 real roots. You don't have to understand all that, but basically you just got to understand that. Look in the book, and it'll look something like this, okay? And so say, here's your function. You got to have a constant here, and you're going to have e to the x divided by this L. So it'll pull this L back here, and it shows up here again. And the L shows up here, and this is e to the minus x over LP. So the book will help you do that. It'll tell you where to plug everything in. So now you have a general solution, but it is not the specific solution for this particular BJT. And so the last step you do with the differential equation is you apply boundary conditions. And I always say that boundary conditions are basically just applying common sense to solve for unknowns. So I've got two unknowns here. I've got C1 and C2, okay? And the only variable I have is x. If I could solve for C1 and C2, I'm in good shape. And so what can I do to start, simplifying this down? Well, when we were in Chapter 4, this was easy to solve. We were basically, in Chapter 4, you solved this at looking at carriers coming into the edge of a semiconductor, just like on the previous page. And so if we were plotting, I'm creating an excess of holes right here, and I look at distance x, we said it went down exponentially with distance x. So here's that, and there's my excess there. And so it had this sort of behavior where it goes to 0. Well, that was easy to solve because I knew the solution was just this, right? Because I have some constant, which would be the excess right here, the delta at x equals 0, and then with forward distance, I know that my holes decrease because they're recombining. So I applied common sense. I know that this must be a solution. I know that this is not a solution, because if this was a solution, it would say that at distance x, as you keep going further with distance x, it would say your holes go to infinite concentration. Well, I know there's no such thing or material of semiconductor where if I increase distance x, the hole concentration increases indefinitely. And so back in Chapter 4, we assumed that C1 was equal to 0. I could eliminate this term using common sense type principles, also known as boundary conditions. Now, unfortunately, that's not what we can do here. Most differential equations, you could do something simple like that and get the solution, which is the same solution we showed on the previous slide of carrier concentration showing up and going into a semiconductor and decreasing with distance. But for the BJT, it's going to be far more complicated. So remember that differential equations are easy to solve, but unfortunately for a device like a BJT, it's going to get more complicated because we don't go infinite distance in a BJT. So we can't assume this goes to infinite concentration, and we cannot get rid of this term because the distance is finite in a BJT, meaning that we're only going from 0 on one side to WB on the other side. So it's a finite system, and we've got to keep these terms and try to solve for it. Okay, so now let's keep working on getting the carrier flow in the base, okay? And so we had solved for these previously. I have an excess at one side, delta PE, and I have 0 at the other side. Delta PC is equal to minus P sub n. P sub n minus P sub n gives me 0. We have this from the previous slide. We solved for this general solution, right? And again, let's apply some boundary conditions to try to simplify this down. Well, we already know that the excess at xn equals 0, right here xn equals 0, is equal to delta PE. So I can say, okay, xn equals 0, I'll substitute x equals 0, this term goes away, I just get C1. Xn equals 0, this term goes away, it comes 1, I get C2. C1 plus C2 is equal to delta PE, because here at 0, we have delta PE. So that's an equation which helps me start to solve for C1 and C2. And I can do the same thing at WB. At WB, I substitute in into x, WB, so there's WB subbed in for x. And I know at that end, at WB, my excess is delta PC, which is minus P sub n. So I set that equal to delta PC. So now I've got basically two variables and two equations. Okay, two variables and two equations. And again, for most differential equations, you'd be done by now. But for BJTs, it's more complex. I've got my two variables and two equations, so I could rework these and solve for C1 and C2. I'm not going to do the math, but you could figure that out. Two variables, two equations. And you solve for C1, you solve for C2. So it's starting to get more complicated, right? Well, it'll get simpler at the end, but just hang in there. So what I'll do is I will substitute my newly found C1 and C2 back into this equation, okay? And I will get the following here. And I've replaced all this stuff with just these m coefficients. So all this stuff here I said is just m, and all this stuff here is just m2, just so I didn't have to write it out and I could write a simpler equation. Well, what you find when you look at this, in terms of all this, is that you basically have an addition of two effects. You have holes diffusing in one side, so it's like a p-n junction where holes show up at one side and they go to 0 with distance. And then at the collector side, you've got like a reverse bias p-n junction where the whole concentration goes to zero, where they're all drifting out the other side. And so you've got two solutions, which when you add them together, gives you a profile which looks somewhat linear. And so here's my actual solution. If I take the diffusing in and the drifting out and I combine them together, and you find something that looks like more like a straight line where these curvatures cancel out. Here's my excess delta PEE, delta PE on this side, and then here it goes to zero at the edge of the base width at WB, because this is the edge of the base. Depletion region for the base collector is starting right here, and this is where the cliff is, where all the holes are drifting out to the other side. Okay, so at this point we're going to pull it all together. Here's the equation, here's the M coefficients, and I can start to plot my carrier concentrations as follows. And these are minority carrier concentrations. This is forward biased, right? And so electrons would show up here, and they would basically be of a lower concentration as they go further distance in, because they're recombining with holes. I'm diffusing over holes this way, I get an excess here. They decrease with distance, normally due to recombination, but for this base, what really brings the population down is at this side, I know it's zero because this is reverse biased, so all the holes that make it to this side fall off the cliff and drift across to the collector. And again, this is a reverse biased diode, right? And so if I look at the minority carrier electrons over here, its profile goes to zero because every electron at the edge of the cliff for a reverse biased diode falls off the edge as well. Okay? And so the question I have for you as a bit of review is what causes the change in concentration of carriers for each of these? Well, if you look below here, you can see that this is diffusion. It's forward biased, so electrons drift diffusing this way, holes diffusing this way. Over on this side, this is drift, reverse bias diode. The minority carrier populations at both sides of the reverse bias diode go to zero because they're all drifting across. And in the middle, my change in concentration here leads to diffusion of holes from high concentration to low, from the emitter side to the collector side of the base. You might ask, why don't we show the excess holes showing up in the collector? Well, we don't care. I mean, we're only showing minority carriers because those are the only concentrations that change. Sure, I inject holes from the emitter into the base and over to the collector. But the number of holes that you inject over here will typically always be well below the doped concentration. So we want to pay attention for this device, the minority carrier concentrations, which we show here, not the majority concentrations. If you look at this, it looks pretty beautiful. You basically have two diodes. One is forward biased, one is reverse biased, and you've joined them together at the base. And so that's all we really see here is a forward and reverse biased diode joined at the base. So, we still haven't told you what the current values are. So, we know that at xn equals 0, we have all IEP. Okay? We assume that we're assuming that hole injection dominates over electron injection this way. So we can assume an emitter injection efficiency of 1. We know that at this end, all the holes that show up here become collector current. And we now have an equation for the hole concentration across the base, this delta P function we derived. So what we can do then, if we want to know what is the current coming across the base, and if we know the current coming across the base, then we can figure out the current injecting here and the current showing up here. We can get the current across the base by basically taking this concentration gradient and putting it into the diffusion current equation. So this, again, the diffusion current equation, my current is equal to, well, here's my coulombs, here's my area, okay, because I want current density times area gives me actual current. Here's my diffusion coefficient, and here's my derivative of my concentration gradient, and here's my concentration gradient. So again, this is the diffusion equation for current, and it basically tells us that as I have a larger change in concentration gradient, as this goes up, and I see a larger slope here, more and more slope, I get more current through the base. So, still working our way to get the current values. I will substitute in that exact profile here, delta P. I'll substitute this into my equation for calculating diffusion current. I put this in there. I take the derivative of this with respect to x, okay, which is easily done. And then I solve for it, given some boundary conditions again. And so I know I can solve for it at xn equals 0, the edge of the base right here. This is the emitter side of the base, xn equals 0. At that point, I have all IEP. That's all this current here, right? Right here, when the holes show up right here, it's all due to the emitter current. So I can solve for my emitter current then by substituting in xn equals 0 into this equation for diffusion current. And my C and C1 and C2, again, x equals 0, these become C1 and C2, and now I've got an equation for my emitter current. On the other end, I want to know what's my collector current, right? Well, if I want to get my collector current, I'll do the exact same thing, but I'll substitute in at this end, x is equal to WB. I put WB in here, and I get a solution for my collector current. Once again, I've got two equations and two variables, C1 and C2, and we're going to derive and solve for everything, and I'm going to skip the math and you'll see why. So, solving for C1 and C2, we'll skip the math, we get the following beautiful equations for the currents in a BJT, and you'll see why they're beautiful in a second, but just bear with me, okay? Here's my emitter current. I've got this delta PE, some semiconductor type parameters here, and some nasty hyperbolic trig functions. Here's my collector current. It looks similar, except I've got some different hyperbolic trig functions here. If I've got my emitter and collector current, how do I get the base current? Well, if I have a circuit here, and I have current coming in here and current coming out here, that must balance with the current coming out here, and so I know my base current is my emitter current minus my collector current, basically summing the currents coming in and out of a node here in a circuit. And so I could take these two, substitute them in here, and I get the following equation, which I can simplify for base current. And so that's it. These are the equations to predict currents for each terminal of a BJT. I want you to hang on. In the next portion of this lecture, I will show you how simple these things actually are. This first portion, we did the derivation and build up our understanding of how the current drives across the base. So, some quick review, and then you could take a break. First off, how do you solve a differential equation? You should be able to tell me the 4 general steps I talked about for how to do that, okay? Second question, the hole concentration across the base, what does it look like? So you can kind of run through these, and you should be able to tell me right off the bat very quickly which answer you have there. You should also know how the current is driven from the emitter into the base, how current is driven across the base from the emitter side to the collector side, and how current is driven from the base into the collector. Okay? Last thing I want you to do before you start the next one is, if I further simplify those terminal current equations down, I can start to write them out like this, and I start to color highlight these things as follows. And so one of the things you might notice is that all of these currents have this delta PE term. And if you look back at what delta PE was, as we had it before, and we had it on the earlier slides, it could be calculated as follows, and it has voltage in it. And so you see that all 3 of these equations are dependent only on VEB, the voltage across the emitter base, and therefore all 3 equations go up or go down at the same rate. So you should ask yourself, does this make sense for a BJT? And if you're thinking about this, it should, because if I have more holes coming up here, I have more holes coming out the collector. So if the emitter current goes up, the collector current should go up too, right? Think about the base current. If I have more holes coming in here, then I'm going to have more recombination with electrons, so I'm going to need more base current as well. Furthermore, remember that the base current and collector current were proportional. You amplify base current into collector current with a proportional amplification factor. So just a constant you multiply times base current gives you collector current. So if base current goes up, collector current goes up at the same rate. And so these equations, and I'll make more sense of them on the next part of this lecture, will start to make a lot of sense, because you'll see that you can break them down into things that are just telling you how the currents in a BJT work.